In this section, we're going to begin a study of vectors. And to get an idea of what vectors are all about, consider this problem. Suppose we have a ship that is heading east at 15 miles per hour. Now, heading refers to the direction that the bow of the ship is facing, not necessarily the path which it is traveling, as we'll see in a moment, because there's a tide affecting the travel of the ship, you see, and the tide is traveling north 10 degrees east at a rate of 5 miles per hour. We want to find the speed and the course of the ship. Although the ship is facing east, it's not actually traveling east because of the effect of the tide. Now, this is the notion of the idea of vector, and both the ship and the tide represent a vector idea because they have involved with them both a speed and a direction. So vector quantities are quantities that have direction and magnitude associated with them. It requires then two real numbers to describe a vector quantity. On the other hand, scalar quantities have magnitude only associated with them and can be described using one real number. Well, to solve the problem, we can bring to bear many of the techniques that we have learned already involving trigonometry. And we're going to take a geometric approach to this problem, and in fact we're going to see a couple of geometric approaches, and then we're going to move into an algebraic approach to the same kind of problem a little bit later. Well, the geometric approach looks like this, or one of the geometric approaches looks like this. We can represent the ship vector and the tide vector using a directed segment. Now, for the ship, it's a segment which has direction given by the arrow at the end of the segment. Now, there's an initial point A and a terminal point B involved with this vector idea, with this little arrow arrangement. The direction of the arrow corresponds with the direction of the ship. Remember, the ship is going due east, so we make our vector arrow, we cause it to go due east, you see. And its length corresponds with the magnitude associated with the ship. The ship is going 15 miles per hour, so we have a certain distance associated with that. Now, since the tide is going in a different direction at a different speed, you see, we have a different arrow direction for its vector, and we have a different length associated with it because it is less, the speed is a little bit less, the magnitude is a bit less. Well, let's see, we have the ship is going 15 miles per hour, so this rascal would be 15. The tide is going at 5 miles per hour, so we can associate it with a number 5. Now, the ship is designated, the notation for the ship vector is AB. The A is written first because it's the initial side. The B is written second because it's the terminal side. And this little notation just simply indicates that it's a vector. And it starts at A and goes to B. So the direction is built into this notation. The tide vector is AC, and again, same idea. Now, these two vectors are called the components of the resulting situation involving the ship. That is, the ship, rather than traveling along this path, although it is heading in this path at that rate of speed, it's not actually traveling along that path. It is traveling along a path which is affected by the tide. So no wonder these are the components of the travel or the path of the ship. But the result of these two components will be a vector which is somewhere between these two, presumably. Now, we can draw the situation like this. We can set up a little parallelogram like this. We can do this. Now, it turns out that the resulting travel or path for the ship will be the diagonal in this parallelogram. You see, now with that idea, we can use either this triangle or that triangle in solving the problem. Now, what we'd like to know is the speed and course of the ship. So we would like the length of that vector, you see, the length of this arrow, and also the direction that it's taking. Now, how can we figure all of that business out? Well, we're using, as I say, either of the top triangle or the bottom triangle. If we use the top triangle, it looks like this. we would be thinking about this top triangle, and this is 15 down here. We have a parallelogram, so this is 15 up top. All right, now we have a couple of distances, or a couple of the sides of the triangle. Now what about this tide vector? Now we know that the ship is traveling due east, but the tide was traveling 10 degrees, let's see, north 10 degrees east. So it's like we have a north-south line here, and this angle is 10 degrees. You see, now if that angle is 10 degrees, let's get into our triangulation here by thinking about that. Now all of this is 90 degrees. We take away 10 and we have 80. So we have 80 degrees here. So that's an 80-degree angle. Now I'm overlapping the two triangles. Gee, we'd like information within one triangle. But we use the idea from geometry that with parallelograms, adjacent angles are supplementary. Adjacent angles are supplementary. So let's see, this angle and that one, those would be supplements, and these two would be supplements. Now using that idea, we can find this angle. Because they're supplements, the sum of their measures is 180 degrees. So we take 180 and subtract 80, and that means that this angle is 100 degrees. All right, now we're ready to go. We're ready to solve this triangle, and specifically we don't want to solve the whole triangle necessarily, although in some cases we may have to, but what we're really targeting is the idea of this resultant vector, you see. Okay, so now we have, let's label this D, and so we're trying to find this distance AD, you see. And let's see, we have information about a side, and an angle which is not related to either of those two sides. So, we can use the law of cosines. Now, using the law of cosines, you know, we're identifying this as our target that we want to solve for. So it's AD squared, you see, is equal to the sum of the squares of the other two sides minus 2 times each of these times cosine of that angle of 100 degrees. Let's go over here and solve it. We have AD squared then is equal to AC squared plus CD squared minus 2 times AC times CD times cosine C. All right, that's just a notation that we can use here. Now I'm using AC rather than something like a single lowercase letter of A or B, which we've seen many times in the past. I could label those sides a little differently, but since we're already set up with a notation for labeling in this vector format, I'm going to use the AC-CD notion here. Okay, so let's see, AC turned out to be 5 CD 15, and AC 5 CD 15, and we have cosine 100 degrees. So we punch our calculator, we find AD squared to be this value, and then the square root then of this we find to be 16.6 miles per hour approximately. So that's the magnitude then corresponding with the ship. That is, the ship is now traveling, we know, at 16.6 miles per hour. It was heading due east at exactly 15 miles per hour, but because of the tide vector, the tide is kind of helping it along a little bit. So it's actually traveling at 16.6 miles per hour. Now we'd like some information about, well, let's see, what do we need information about? We come back over here and we're thinking, well, we have information about the length of this side telling us about the speed, the actual speed of the ship, but we need kind of an angle right here. Oh, we can find this angle then. Now this angle is opposite that side. So we can use now the law of sines because we have this angle and side opposite pair that we already know about. So we come back over here and we set it up this way. The sine of that angle theta, I'm calling it theta here. Let's come back over here. I'll label it properly. Let me see if I can here. I'm pretty jammed with a lot of information, but here's what I'm doing. The angle theta that I'm talking about is this angle theta. Now we have 100 degrees up here. So it's going to be the sine of theta over 15 is equal to the sine of 100 over this is 15. This is a little bit confusing. Let me take this off. This 15 is down here at the bottom. Now this side we just found to be approximately 16.6. Okay, so it's the idea that we have the sine of theta is to 15 as the sine of 100 degrees is to 16.6. So that's the idea. So sine theta over CD equals sine C over AD. So sine theta over 15, sine 100 over 16.6. We find theta to be approximately 62.8 degrees. But do we want theta? Is this the course of the ship? Is that how we describe the direction that the ship is traveling? Well, not exactly. Let's come back over here. You see, we have, let's see, if this theta is 62.8 degrees, and we know that this was 10 degrees, then we add those together to give the actual direction that the ship is traveling. It turns out to be 72.8 degrees. So we summarize and say that the ship is traveling 16.6 miles per hour on a course of north 62.8 degrees east. All right. Now, as I mentioned, there are a couple of geometric ways to set this up. Some students prefer to do this. They prefer to use more of a nose to tail kind of configuration. And this is what that's all about. Now, the previous problem was set up using the parallelogram approach because that was the kind of the nature of our overall diagram. But here, the nose to tail idea works like this. If we begin with one of the vectors like, oh, let's say the ship vector. So the ship at 15 miles per hour going due east, and then we have the tide vector affecting this, and we just attach the other vector at the end of this one. We make the initial side of the tide vector occur right here, and then send that tide vector in its appropriate direction up this way. So here's the tide vector, and the tide we know is going 5 miles per hour. Okay, now recall that the tide vector is going at an angle of 10 degrees. So this angle right here would be 10 degrees. Now what we want as the result of these two component vectors is a vector which goes from the beginning of the first one to the end of the last one. And I want to say it like that because we could have some kind of problem where we have a number of vectors in play, not just two, we could have 5, for example. And if we use this nose to tail idea, then we just kind of connect them all together and we go from the initial point, you see, from the initial point of the first vector to the terminal point of the last one. And that becomes our resultant idea. Okay, so we want this then, you see, as our resultant. And it's a problem very similar to the one before. That is, we have information about, let's see, these two sides, and this angle turns out to be, well, this is 90 degrees up to here, and that's another 10 degrees, so this angle turns out to be 100 degrees. And now we kind of look at it from the standpoint of law of sines or law of cosines. We have information about this angle, but nothing about that opposite side. And we have information about the other two sides. So then we determine that we have to use the law of cosines. We would use it in exactly the same way that we did before. And our labeling could come into play here and so forth. But we would find then, using exactly the same law of cosines we did before, this side to be 16.6 approximately. Right, then we want a direction associated with this, so we're working within our triangle here, and our angle theta then is this angle. And to find the size of this angle, we do this. We set up the law of sines because we have an angle side opposite pair. So it would be sine of the theta we're talking about here corresponds with side opposite 5. And I'm going to go ahead and fill in as I go here because I think we've seen this enough times before to where we can do this. And the sine of 100 degrees is to the side opposite 16.6. All right, and then solving this, multiplying by 5 on both sides and resolving this with the calculator, we find sine theta to be a certain fraction, and theta is the angle whose sine is that fraction, and that angle we find to be approximately 17.2. But is that the angle that we want in this problem? No, it's not. We want to give the course of the ship in a direction format consistent with the direction that we had for the tide and for the ship initially. So it is a direction off of a north-south line. So that's north, this is south. And so it would be north so many degrees toward the east, you see. And so we really need this angle. And to find that angle, we take theta and subtract it from 90 degrees. So we go 90 minus 17.2, and we find that direction to be, as we did before, 72.8 degrees. In the previous problem involving the ship and the ship vector and tide vector were considered to be components, and we were looking for the resultant vector. Well, it's often the case that rather than looking for a resultant vector given components, that we're given a resultant and we're looking for components. We can actually subdivide resultants into components in a rather special way. Now, let's understand generally what that would entail. If we have a resultant vector like this, there are actually an infinite number of components that could give us this resultant. And if we're only looking for two components to give this resultant, I could do it like this. I could illustrate using this nose to tail kind of configuration. I could say, well, we have one vector like this and another like this as the components for that resultant. Another would be, well, maybe one like this and like that. You see, those components could give this resultant, and there are an infinite number of others. Well, it's often the case when we're looking for components, those components need to be written as horizontal and vertical components. And it turns out that that's pretty easy to do. That is, if we have a resultant of 50 miles per hour at 60 degrees, then we have this kind of configuration. And to calculate horizontal and vertical components, we just set up a little right triangle configuration here. Because we have, let's see, the components for that resultant can be considered to be this horizontal component and a vertical component that goes up here, but I could draw it right here for calculation purposes. You see, so we just have a right triangle set up. We have an x and a y. An x for horizontal distance or magnitude, and a y for vertical magnitude. All right, for the x component here, for the horizontal component, you see, it's the cosine of 60 degrees, that's x over 50. So cosine 60 degrees, x over 50, x then is 50 cosine 60 degrees. For the vertical component, from the perspective of the 60-degree angle, we're involving y with 50, opposite side over hypotenuse. So it's the sine of 60 degrees that is y over 50, so y then is 50 sine 60 degrees. Now, the important thing to notice here, generally, specifically we're going to make the calculations here, but generally speaking, we have for our horizontal component, we're involving the magnitude of the resultant vector and the angle that was given, you see, for the resultant vector. And it's important to know that just with that bit of information, we can calculate a horizontal component. And in a similar way, the vertical component is the given magnitude times the sine of the given angle. So that's the general idea. And if I put labels on these general values here, then x would be r, often is used for magnitude, and this would be cosine of theta for a general angle. So that's the notion. Now, specifically, let's assign some numbers here because we're dealing with a specific problem, but 50 times cosine 60 degrees turns out to be 25, and that's 25 miles per hour. And then 50 sine 60 would be approximately 43.3 miles per hour. Now let's talk about some notation. Here's how vectors are given or written a lot of times. A vector can be written in its component form, in its form of horizontal and vertical components, you see, like this. Now, notice the notation of this little symbol on either side here. And the horizontal component is r cosine theta. The vertical component is r sine theta. And for our problem, it would be 25 comma 43.3. And notice the horizontal and vertical idea. Gee, this corresponds really well with our notion of ordered pairs and our coordinate plane and all of that kind of thing. So it's very consistent with that and easy to recall. So a vector in its component form would be kind of an xy pair here, given by mostly this r cosine theta, r sine theta notion. Let's talk about a problem on the coordinate plane. Now, we want to express u in terms of horizontal and vertical components. Now, just looking at our coordinate plane here, we can set up a right triangle configuration and make the calculation very quickly. That is, all we have to do in terms of horizontal and vertical is do this kind of thing. You see, and we have a right triangle formed, and it's real easy just to count here if we want to, and count here for horizontal and vertical components. Now, the calculations, though, need to be made in a rather special way. We have direction associated with problems like this, and so when we make the calculations of, now notice for the horizontal value, it's horizontal distance minus this horizontal distance to give us this horizontal distance. So it's 7 minus 2, and it's important to perform the operation in a particular order. We actually use the components of, I shouldn't say components because we use that same word elsewhere, but the coordinates of our terminal point minus the coordinates of our initial point, you see, in this calculation. So 7 minus 2 for the x value, and 5 minus 3, the 5 coming from here and the 3 from here as the vertical value. So 5, 2. Now, the magnitude, let's stay right here for just a second. The magnitude of our resultant vector can be found rather easily because we have this right triangle configuration, and we've determined that this side is 5 and this side is 2. Gee, we can use the Pythagorean relationship, you see, to find the distance here. And it would be, let's see, c squared is 5 squared plus 2 squared, or c is equal to the square root of 5 squared plus 2 squared. Now let's generalize that idea. We're dealing with vectors here, and we're talking about the magnitude then of u. So the magnitude of u has this notation. This is the magnitude for u, and it's the square root of the horizontal magnitude, that h we were talking about, squared plus v squared. And in this problem it's 5 squared plus 2 squared, or the square root of 29. Now, what about the angle involved? Well, when we talk about a coordinate plane and we get away from the notion of navigation, where we think about angles off of a vertical or a north-south line, we think about angles from the horizontal. And remember that this just corresponds with our study of trigonometry from the beginning, where we had angles in standard position and all of that kind of thing. So we're just looking for this angle. You see, and we're thinking of it generated like that. Okay, so we're looking for that angle. We have information about opposite side and adjacent side. Now, we calculated the hypotenuse, but gee, with just the given information, we can make the calculation for theta using the tangent ratio. So it is that the tangent of theta is the vertical component over the horizontal component, the y over x, you see. And tangent theta then for our problem is 2/5. Theta turns out to be approximately 21.8 degrees. All right, more notation here. The u, that resultant vector, can be written in component form as horizontal and vertical components. And for our problem, it was 5, 2. The calculation can be made in problems like this as r cosine theta, r sine theta for the horizontal and vertical components. Now, we didn't need to make the calculations this way on this problem because we were given information on the coordinate plane and we were able to figure out the 5 and the 2 rather easily. But if we're writing the situation using this kind of designation, then we figured out that the magnitude of our vector u was the square root of 29, and the angle was 21.8 degrees. So we could actually fill in here for these two. Now, I do want to tell you that we see the square root of 29 here and the square root of 29 here, and we can actually factor that or extract that from this notation and say this is the square root of 29 times, you see, sine 21.8, cosine 21.8 degrees, comma, sine 21.8 degrees. This kind of brings us to the point of vector operations. Operations on vectors are pretty much as we might expect. For example, if we have vectors v sub 1 and v sub 2, and v sub 1 is defined in its horizontal and vertical component form as AB, and v sub 2 is CD, then the sum of the two vectors is found by simply adding the horizontal components and adding the vertical components, you see, and here's the component form of their sum. For multiplication, once again, pretty much as we would expect, if v is AB, then 5v means 5 times AB, or 5a comma 5b. It turns out that vector addition can be used to resolve the original problem that we talked about. Now, in that problem we had a ship and a tide, and we said that the vectors corresponding with the ship and the tide were components, and we wanted the resultant. Well, those components were not in this algebraic component form having to do with horizontal and vertical. They were just the components, and we were looking for a resultant. Let's approach the problem algebraically and rewrite the information about the ship and the tide in a horizontal and vertical component form, and then handle the solution algebraically. Well, for the ship, now in horizontal and vertical component form, we have a magnitude of 15 and an angle of, well, gee, if the ship is going due east, then the angle is simply 0 degrees. So it's 15 cosine 0 degrees for the horizontal component and 15 sine 0 degrees for the vertical component. Now cosine 0 degrees is 1, so this is simply 15. Sine 0 degrees is 0. 15 times 0 is 0. And just kind of intuitively we would expect this for the component form of the ship vector, because after all the ship is going due east. So the horizontal component, you see, would correspond with its magnitude, and the vertical component would be simply 0. Okay, for the tide, it's a kind of a different kind of thing here. We're not going to get this a nice, easy situation, but here's how we handle it. The tide is going 5 miles per hour on an angle that is north 10 degrees to the east. Now, we want magnitude times cosine of an angle, but the angle is turned from the horizontal. Remember, it's turned up like this. We're thinking of, you see that tide vector was like this. I'm overemphasizing it with a larger angle than 10 degrees here, but that's the information that we're given. But what we really want is this angle. You see, so we take 90 and subtract 10, we get 80 degrees, and that's why 80 degrees is used here. So we have 5 cosine 80 degrees, 5 sine 80 degrees, and we could actually approximate these values at this point if we want to. But we're going to use this in a further calculation. So let's leave this information in this form. It turns out that the resultant vector in this problem is found by simply adding these two. So it's s plus t for the resultant, which I've labeled R here. And we're adding the items that's in corresponding positions here. Add the horizontal components, add the vertical components, you see, and we get this. Now there is a decimal equivalent for each of these, and notice that I'm writing them in a really long-winded decimal form because we have additional calculations that need to be made. I wanted to show this approximation, though, to give some feeling for horizontal and vertical components involved in this resultant vector. Now let's make the calculation for magnitude and direction involved in this resultant vector, which is the course of the ship. All right, so we have this horizontal, vertical. Remember, the magnitude is designated like this. This is the magnitude of that resultant little vector, and it's the square root of the sum of the squares of the two components. And so I've written them in here with the dot, dot, dot because I didn't want to write all those digits. And when we perform the calculations, we get approximately 16.6 miles per hour as expected. For the direction, we use the tangent idea. The tangent of theta is y over x, or that 4.2 decimal and the 15.8 decimal in the denominator. And we find theta to be approximately 17.2 degrees. Now just realize, though, that this 17.2 degrees is an angle from the horizontal. That is, it's more like this is the 17.2 degrees. And if we want to write this angle in terms of navigation, that is, some angle off of north or south, then we would need to calculate this angle, and that's what we did before. It was 90 minus this for that angle off of north. Okay, so that's the idea. Now just generally though, realize that what we have done here, we have, for this algebraic form to take place, we have taken our two vectors associated with the ship and the tide, and we have rewritten them in terms of horizontal and vertical components. And then we simply added them together. We added them algebraically. And then once we get an answer to that, then the resultant is in horizontal and vertical component form. But then at that point we have to go back and make the calculation for magnitude and angle, you see. So there's a kind of a flow to it, to problems that are performed algebraically. Okay, notice this notation. If we're talking about a vector that is, let's say an object is traveling at 100 miles per hour on an angle that is 30 degrees from the horizontal, you see, and in this direction, then there are a number of ways to indicate this situation as a vector. One way is to say, well, it's the magnitude 100 times cosine angle sine angle. Now the angle, notice, that's used here is not 30 degrees because it's the angle from standard form, you see. So it's this angle. It's 180 plus 30 or 210. Another way to represent it would be 100 times each of these, so we would have this representation. Now we know that we can calculate the cosine of 210. It's actually the cosine of 30 in the third quadrant, and it's negative the square root of 3 over 2. And here for sine 210 it's negative 1/2. So simplifying just a little bit, we find the component form to be negative 50 root 3 and then negative 50. Now another notation that is often used in this situation, and it's more algebraic in nature than the notation that we're using here. Now this is the truly vector notation with these little indicators on either side. But we can just associate each of these components, the horizontal and vertical components, with a letter that's like a variable. And notice that I've written this as the coefficient of a letter I, and this as the coefficient of a letter J. And using this I and J and understanding the convention that the coefficient of I is a horizontal component and the coefficient of J is a vertical component, then we can make the additions. You see, we can add, we can manipulate in this form perhaps more easily in some situations than we could in this form. So it's just a variation on the same theme. Take a look at this problem. Here's a problem involving three force vectors. Three forces of 75 pounds, 100 pounds, and 125 pounds act on the same object at angles of 30 degrees, 45 degrees, and 120 degrees respectively with the positive x-axis. Now the reference to the positive x-axis simply means that our angles are measured in the conventional sense as opposed to the nautical sense. Find the direction and magnitude of the resultant force. Well, let's imagine an object such as this object, and we might imagine some attachment point on the object or some point at which the various vectors are in play. And at that point we might imagine a coordinate system and the origin of the coordinate system. Then we can represent the various forces involved. Now notice that the angles here involved in the coordinate system correspond to the angles that were given in the problem, 30 degrees, 45 degrees, and 120 degrees. And the lengths, of course, of the arrows correspond to the magnitudes. Well, let's label these V sub 1, V sub 2, and V sub 3 for our three vectors. There are a couple of ways of proceeding from here. One way is to think of the problem in the nose to tail format. So we would restructure our figure like this. Now this format is very handy in estimating the kind of answer that we're going to get. We know that the resultant vector will be in this position. Now let's call the resultant V. Now from this diagram, you see, we can estimate that V is, a little less than double V sub 3. So we might be able to estimate it to be somewhat less than 250 pounds, you see, 220 to 240 perhaps. And then we might estimate the angle as being, between 45 and
and 90 degrees, it's certainly greater than 45, certainly less than 90, maybe 70 degrees. So in this way we could come up with a pretty good estimate of our answer. Actually, trying to set up various triangulations here to use our trigonometric tools is a little bit of a cumbersome process. What we might do is list our vectors in component forms. Now here's one way to do that. Notice the magnitudes are coefficients here of our two unit components here in our symbols of inclusion. So this is just another way of listing the component form. Now multiplying the magnitudes times each of the two portions in the symbols of inclusion, we would get these. Now from this component form, from this component format, we can figure the resultant this way. Simply add the three first components and add the three second components, and this is what V is all about. This is the resultant V. So this is the V in the resultant in component form. Well, all we need to do now is figure the magnitude and direction involved from this component form. Well, the magnitude is found by taking the square root of the sum of the squares of the two components. And by heating up our calculator a little bit, we find that the magnitude is approximately 228.5 pounds. Now for the angle, we use the tangent function, and it's simply second component over first component. And the ratio on the right becomes 2.96. Now take the inverse tangent on both sides to find theta to be 71.3 degrees. So now we have our magnitude and our direction, and we can write our answer. The resultant is a force of 228.5 pounds acting at an angle of 71.3 degrees.
Sometimes I think that the confusion in trigonometry, if there is any, emerges because we have a lot of different notations to kind of keep straight. They're equivalent to one another, and yet there are so many of them that we may have trouble keeping them straight, and we have little branches that we kind of go into in our study of trigonometry, and they could add to the confusion as well. Now, in an effort to try to clear up some of that, I want to talk about a topic that is addressed in your textbook. It's mentioned a couple of times, and it's unit vector. Now, the notion is this, that if we have a vector v that has this component form, then a unit vector related to this would be a vector whose magnitude is 1. That's the notion of unit anything. Unit circle is a radius of 1. Unit vector, a magnitude of 1. Now, if I want to transform this vector into a unit vector, that is a vector whose magnitude is 1, but whose direction is exactly the same as this one, then I can do that in a couple of ways. And I want you to understand the concept of making this transformation. There is a tendency when there is some confusion in a subject like trigonometry to resort to memorization. You think, well, gee, what do I have to do to accomplish this? And I'm really scared about the situation. And so you try to memorize some stuff, and then that becomes even more confusing. So let's try to grasp the concept of the idea that the -2 and the 5, the component form, contains information about magnitude. And in fact, one of the ways to write the component form for a vector v would be r cosine theta, r sine theta. Recall that? And the r is magnitude. So the magnitude is sort of contained as a factor within each of these. And if we want to write a unit vector, all we have to do is sort of divide out that magnitude. You see, that's the concept. So here's what we're doing. The unit vector, that is a vector whose magnitude is 1 but goes in the same direction as v, would be found by just taking the -2 and dividing by the magnitude of v. 5 divided by the magnitude of v. Now, the magnitude of v is found like this. As you recall, the magnitude is the square root of the sum of the squares of each of the components. So in this case, it would be the square root of 29. So we could actually write the unit vector then as negative 2 over root 29, 5 over root 29, or we could kind of extract 1 over the square root of 29 like this and write it in this form. And this is an interesting form because notice that the negative 2, 5 is just the component form of v that we just first started with. So this is just 1 over the magnitude associated with this vector in component form. Okay, so that's the idea. Now I'm not trying to, in writing this step, I'm not trying to emphasize that we're trying to identify cosine theta and sine theta. Although we do end up with that calculation in this part of the problem, you see. So this fraction would indeed be cosine theta. This fraction would indeed be sine theta because we are dividing out that idea of magnitude. Okay, so just a lot of ways of looking at the same situation. Now, unit vector might be important in problems where we're looking for the direction angle only. And if we're looking for that angle only and we're not concerned with magnitude, then we could just look at the unit vector associated with a particular vector. Now, often though, it's not worthwhile to go through the process of calculation for the unit vector for that purpose, but we'll see other uses for unit vector in the future. Okay, consider this problem. I'm showing this problem because, once again, there is something that may be confusing here, but is consistent with what we've been talking about. And the possible confusion is the notation for the vector v. Let's just find the direction angle of v equals 3i minus 4j. Now, I mentioned this algebraic form that we can use in dealing with vectors, in describing vectors. But just to understand that this means the same thing as in component form 3, negative 4. You see, it means exactly the same thing. It's just that this is a more algebraic form, maybe more manipulative in the algebraic sense than this might be. Now, it's not just a matter, when we use this form, it's not just a matter of attaching letters to those two. It kind of looks like it and we can kind of think of it like that. But to be mathematically sound, we have to realize that I and j are not really variables here. We're going to treat them like variables for manipulative purposes, but they're not variables. What they are, and if we define them properly, if we're thinking about, well, let's see, we have a horizontal component here and a vertical component here, so gee, this is a horizontal component, and this must be something that's like a unit horizontal component, you see. And indeed, we could define I to be 1, 0, you see. This would be like a unit horizontal vector, and this would be a unit vertical vector. So j could be defined as 0, 1. You see, just for concise mathematical purposes, we would do that. We don't refer back to this very often, but it's important to know that it's there. Okay, now understand what we mean by direction angle. If we're talking about this vector, either in this form or this form, we can describe it here. We can draw a diagram consistent with it. And it would be a vector that starts at a particular point and has a horizontal component of 3 and a vertical component of negative 4. It's convenient in analyzing vectors to start at the origin and draw the vector from the origin. But really, we could draw that vector from any spot that we want to. Yeah, let's understand that. We're just electing to draw it from here. You know, it is the case that vectors have characteristics of magnitude and direction. But that magnitude and direction can be taken from any spot that we want to on the coordinate plane. All right, now the convenience of using the origin as the initial point of the vector is that it's really consistent with our idea of coordinates and so forth from our past studies. Okay, so we go a distance of 3, horizontal component 3, vertical component negative 4. So the vector then looks like this, and we want the direction angle. Now, the direction angle, gee, if we're thinking about a standard form of direction angle, then we would be talking about a direction angle that's measured like this. You see, we want that angle. Okay, now let's see if we can find that angle. We know from our past study that we have a way of calculating magnitude and direction by using a couple of little relationships that we discussed. And the one for the angle is tangent theta is equal to, and there are several ways of looking at the fraction over here. It's the vertical component over the horizontal component. It is, if we want to write it in terms of trig ratios, it's sine over cosine. Well, we knew this before. And this is consistent with the idea of that unit notion a few moments ago, that if we take the r's out of that r cosine theta, r sine theta, then we have simply sine theta over cosine theta. You see, left for our vertical and horizontal components. So all of this kind of makes sense and blends together. Everything dovetails together in this whole study. Well, at any rate, if we're making the calculation right from the information given, we would just say tangent theta is equal to -4 over 3. Now, and in the calculator, we want the inverse tangent of -4 over 3, and the calculator then tells us that theta is -53.13 degrees. Well, this is a reference angle, and it's a negatively measured angle. It's the angle right in here. And what we really want is the angle measured from here. So what we do is to calculate the coterminal angle in a positive sense with this angle, this negative angle, is we just add 360 to it. So we would just say theta then is 360 with that -53.13 degrees, and we find the angle we want to be 306.87 degrees. We're going to watch some video of space shuttle operations as I lay out this next problem. The space shuttle is composed of 3 parts. One part would be the 2 solid rocket boosters. We'll consider that as one part. Another part is the orbiter. And a third part is this big external fuel tank that provides fuel for 3 engines that are on the orbiter. Now this problem is about the solid rocket boosters. The space shuttle boosters are the largest solid rockets ever flown, and they develop over 2.5 million pounds of thrust. They're also the first rockets designed for reuse. The boosters are jettisoned from the main part of the vehicle 2 minutes after liftoff at an altitude of almost 30 miles. Now, commercial airliners fly at just over 6 miles high. At any rate, the ejection occurs, and then the boosters are recovered after a splashdown in the Atlantic Ocean. Now, after ejecting the boosters, the orbiter, along with the main external fuel tank, fly on. But at the moment of release, the boosters are no longer under the influence of rocket thrust. They're in free fall. And we can make some remarkable trigonometric calculations concerning time and distance as the force of gravity brings the boosters back to Earth. Let's review the situation at the moment of release of the solid rocket boosters. At that moment of release, the shuttle speed is 3,500 miles per hour, the angle of ascent is about 30 degrees, and the altitude is 156,000 feet, or about 30 miles, as we mentioned earlier. Now, the most remarkable thing about this, these numbers are really impressive on their own, but all of this is achieved in 2 minutes of travel. In 2 minutes, the shuttle is going 3,500 miles per hour. Now that's many times the speed of jetliners. Jetliners travel 500, maybe 550, and this is 3,500 miles per hour in 2 minutes, and then 30 miles high. I mean, this is really an impressive set of information about the space shuttle. Now, we're going to make some calculations here about the solid rocket boosters. We're going to calculate the time to splashdown, and we're also going to calculate the distance downrange from this point of release for that splashdown to take place. We're going to have to make a couple of assumptions here because there's a little more math in it than we're capable of providing at this point. And speaking of math, we're not making any calculations prior to the release of the solid rocket boosters because the math involved before that time is really calculus. Calculus is the language of change. There's a great deal of change that goes on from liftoff to this point of release of the solid rocket boosters. But as soon as the boosters are released, it's a vector problem, and it's in our backyard. It's all trigonometry. So we can make some interesting calculations. Now, in order to do that, we have to start with the idea of horizontal and vertical velocity, and therefore we need the components involved in our problem. So let's make the calculation for vertical and horizontal components. Now visually or graphically, we know that our vehicles, our two solid rocket boosters, are traveling with the orbiter and so forth at 3,500 miles per hour on an angle of 30 degrees. And we want to find out how fast those vehicles are traveling. I say those vehicles because I'm kind of separating the idea of the solid rocket boosters now because they are released. So they're traveling horizontally and they're traveling vertically at that moment of release. And then let's make those calculations. So the vertical component is, well, let's see, we have a fast way to do this, but let's understand where that fast way comes from. It's the idea for the vertical component from the perspective of the 30-degree angle, it's opposite over hypotenuse. And that's the notion of sine. So sine 30 degrees is V over 3,500, and that's what gives us this vertical idea of 3,500 sine 30 degrees, which turns out to be 750 miles per hour vertically. All right, the horizontal component. How fast are we going this way? Well, let's see. From the perspective of the 30-degree angle, it's the adjacent side over the hypotenuse, so that's the cosine idea. Cosine 30 degrees is h over 3,500, or h is 3,500 cosine 30, which gives us a horizontal velocity of over 3,000 miles per hour. So at this moment of release, these two things are going on. The solid rocket boosters are still rising at 1,750 miles per hour. And they're headed downrange at over 3,000 miles per hour. Wow. Now, immediately, gravity starts to take effect. And gravity is taking effect on this vertical component. You see this vertical velocity, it's going to start slowing down right away. These solid rocket boosters are. And so they're going to continue going up, and then they're going to slow down, and they're going to kind of come to a stop vertically, and then they're going to begin to fall. And gravity is going to take an effect and pull them down, and they're going to accelerate, and they're coming back down to splashdown. And we want to know the time that it takes for all of that to happen. Now, we're going to make a couple of assumptions here. And we're going to do the vertical part first, and then we'll talk about the horizontal part. But concerning the vertical part, we have to assume information about the difference in the pull of gravity at that level, which is right on the edge of the stratosphere, and gravity here on Earth. Now, it turns out that gravity is not so very much different even at 30 miles up. It's a little bit different, but it's not significantly different. The thing that is significant about this problem, and an assumption that we have to make, has to do with the resistance of the air. You know, the resistance of the air is caused by the vehicle and or the solid rocket boosters encountering little molecules, and those are molecules of oxygen and nitrogen and so forth that happen to be in the air all over the place. Well, we're up at the stratosphere level, so there aren't very many of those molecules, but we're going at 3,500 miles per hour. So we're going to encounter a great deal of them in a short period of time. So there will be a rather significant amount of air resistance, and we are ignoring that here. There are ways to calculate that, by the way. There are formulas having to do with that, but we'll leave that to NASA. We're going to just assume that we don't have air resistance, and we're going to make a calculation. Now, let's go with that calculation. And to make the calculation, we need a formula having to do with height and initial velocity and time. And this is that formula, and this formula is derived from one of Newton's laws. Now, from the perspective of the solid rocket boosters, the surface of the Earth is 156,000 feet below, and therefore the h is negative 156,000. And initial velocity means how fast are we going vertically, you see, and we are going 1,750 miles per hour vertically, you see, and then the t is time, and away we go with our problem. We do have one challenge here, though. We have to have some consistency in our units. This is in feet, and this is in miles per hour, So we either need to decide to go with miles per hour and change this into miles, or we need to go with feet per second, you see, feet and seconds, and change this into feet per second. And that's what I've elected to do here. Now, to change 1,750 miles per hour into feet per second, we have to change the, let's see, the miles into feet by multiplying by 5,280, and then change the hours into seconds by dividing by 3,600. So we divide by 3,600 and multiply by 5,280, and we get this. So the vehicle is traveling at 2,567 feet per second. All right, I really don't need the plural here. Okay, if we want to solve this then for t, it's a quadratic equation, so we're going to throw all the terms to one side. I've elected here to throw the terms to the left side to have a leading coefficient which is positive, making it a little easier to identify the a, b, and c to input into the quadratic formula. Really doesn't make any difference which side we put it on, we're going to get the same result anyway. Okay, so we find t to have a couple of values, one of them positive, one of them negative, and we want the positive value, and it turns out to be 207. And since we're talking about a time here in seconds, it's 207 seconds, which is about 3.5 minutes. So it takes 3.5 minutes for the solid rocket boosters to go from that point of release all the way back down to splashdown from 30 miles up in the air. Now let's understand that in this process, the rockets are still rising. At the point of release, they're still going up at 1,750 miles per hour. Gravity starts to take effect and starts to pull them down, slow them down, and then cause them to come back to Earth. But they continue to rise for a time. And the path that they take is kind of an arc path like this. And that arced path has a top to it. The top is called apogee. And the apogee is reached after about, it's 70 something or 80 seconds, something like that, but it's over a minute. So the solid rocket boosters continue to climb for more than 1 minute and some number of seconds, and then starts to come back down. So this part of this 3.5 minutes of travel is spent, the first minute or so is spent still going up, you see, and then after that it blasts on down. Well, oh, and by the way, that point of apogee is another 100,000 feet above this mark of 156,000 feet. So it goes up to 250,000 feet and more before it actually starts to come back down. And it comes down in a rather big way, a rather fast way. And also in this whole process, I mean, there's certain dynamics here that we're not talking a great deal about, but the solid rocket boosters don't just come right down to the ocean and splash right down into the ocean and then they recover them. If they did that, they would be damaged in a rather big way because they're traveling at a very high rate of speed at that point. So what they do is they put parachutes onto the solid rocket boosters, and those parachutes are deployed, and the deployment starts actually 3 miles in the air. They're coming down pretty fast at that point. And then a little drogue chute goes out, and then the big chutes come out, and so they drift slowly into the ocean. That's really how it occurs. Okay, let's talk about the horizontal idea. And the horizontal idea is the notion of how far downrange from the point of release can we find those solid rocket boosters. And once again, we're ignoring air resistance, which is a pretty big deal in this situation, but we have to ignore that because we don't have the math for it just at the moment. Okay, so ignoring air resistance, this is the way we make the calculation. It turns out that horizontal speed is the same throughout this period of time, throughout this 3.5 minutes. So we can just use our distance formula. Distance is rate times time. Now the rate horizontally is 3,031 miles per hour, and the time is 3.5 minutes. Now again, we need consistency with our units here, and I've elected to change everything into into miles and hours, so I'm changing the minutes into hours. And it becomes 0.0576. Multiplying here, we find the distance downrange to be about 175 miles. So 175 miles downrange, and after 3.5 minutes, we can find those solid rocket